Hi there, welcome to my channel. In this video, I'm going to discuss about the solution to flatten the binary tree to a linked list. Let's look at the problem description. We are given a root of a binary tree and we have to flatten that tree into a linked list. The linked list should use the tree node structure, and in that the right child's pointer will be used as the pointer to the next node in the linked list. The left child should be set to null. Also, the linked list should be in the same order as the pre-order traversal output of the binary tree. Okay. Let's take a look at the example 1. So in this, the binary tree has 6 nodes, and if we do a pre-order traversal, so the output will be 1, 2, 3, 4, 5 and 6. We have to use the right child pointer as the next pointer in the linked list, so it will be like a right skewed tree. Okay. The constraints are the number of nodes in the tree is in the range from 0 to 2000, so the tree may be empty, and each node's value ranging from -100 to 100. There's a follow-up question: can you flatten the tree in place with order of 1 extra space? Let's look at the approach to solve this problem. So we are given this input tree and the expected output is 1, 2, 3, 4, 5, 6. Okay. So basically the pre-order traversal output of this tree. Since we are expected to create the linked list in the order same as the pre-order traversal output, so we have to perform the pre-order traversal on this tree. And when we do pre-order traversal, we process the parent node first and then the left and then the right child. We have to create the linked list by altering the links in the existing tree without allocating a node. Okay. So in that case, whenever we process the node, we try to save the left and right child pointers in a temporary variable and alter the current node's left and right child pointer. And how do we keep track of the linked list? For that, we pass the pointer to the last node in the linked list to the helper function. So basically, whenever we process a node, we have to make a call to a helper function which takes this current node's pointer and also the last node pointer in the linked list built so far. Okay. Inside that helper function, we check whether the last node is null. That means the list is empty. In that case, we just simply assign the current node as the last node. Otherwise, we make the current node as the next node of the last node and update the last node pointer to point to the newly added node. Okay. And then once that link is modified, then we check whether the saved left child pointer is null or not. If it is not null, we make a call recursively to process that left child. Similarly, we make a recursive call to the right child if it is not empty. So at the end of the pre-order traversal, when we come back to the root node will be the head of the linked list where the right pointer will be pointing to the next node in the list. Let's look at the flowchart. The input for this flatten helper procedure is the root node's pointer and pointer to the last node in the linked list created so far. So inside the helper function, first we check whether the root is null. If so, we simply return. Otherwise, we initialize the left and right variables. Basically, they will contain the right child pointer and the left child pointer of the current node. Then we check whether the last pointer is null. If it is null, then we make the current root node as the last node because the list was empty. So the current root node is the first element in the linked list. Otherwise, we add the current root node to the linked list and update the last pointer. Once that parent node processing is done, then we check whether the left is not null. If so, make a recursive call to process that left child. Otherwise, we go ahead and check the right child. If the right child is not empty, then we make a recursive call to process the right child, and then eventually we return. Let's move on to coding. First, I initialize the pointer to the last node in the linked list to null. Then I make a call to the helper function, which takes the root node and the address of the last pointer. Next, I'm going to write the helper function. That takes the pointer to the tree node and then pointer to the last node pointer. First, I check if the root node is null or not. If it is null, I return. Next, I save the left and right child pointers in the left and right variable. We need to save this because we are going to alter the links in the current node. So next I check whether the last node is null. That means there is no element in the linked list. So I assign the current node as the last node. Otherwise, I update the links of the last node in the linked list. So the last node's left pointer will be set to null and the right child pointer will be pointing to the current root node. Then I make the current root node as the last node in the linked list. Next, if the left child is not null, then I make a recursive call to process the left child. And if the right child is not null, then again I make a recursive call to process that right child. Next, I am going to run the test cases. All the tests passed. Next, I am going to submit this program. Cool, this program is accepted. Next, I am going to do the code walkthrough with sample input. We are given this input tree and the expected output is this linked list. Okay. So first we call the flatten functions with the root node, and in that the last node's pointer is initialized to null. Okay, and then we make a call to the flatten helper function with the root node and then the pointer to the last node in the linked list. So initially the linked list is empty, and when the flatten helper function is called, the frame 1 is created in the call stack. So the root is pointing to 1 and the last is null, and the left child of the current root node is 2 and the right child is 5. So in the flatten helper functions we check whether the last is null. In this case it is null, so we simply make the root node as the last node in the linked list. So the linked list has now only one node, and the last is pointing to that node. After that, we check whether the left is not equal to null. In this case, it is not null, it is pointing to the node 2. So we make a recursive call to process that left child. The frame 2 is created now, and the root is 2, and the last node is pointing to, last pointer is pointing to the node 1 in the linked list. And for this node, the left and right child is 3 and 4. Okay. Then we check whether the last is null. In this case, it is not null, it is pointing to 1. So we add the current node to that linked list. First we nullify the left pointer of the last node in the linked list, and then update the right pointer of the last node to point to the current root node, and then finally we make the current root node as the last node in the linked list. So the last pointer is now pointing to the current root node. Then we check whether the left child is not equal to null. In this case, we have node 3 as the left child, so we make a recursive call to process that left child. So the frame 3 is created. In that, the root node is 3 and the last pointer is pointing to the node 2, and this node do not have any children, so the left and right variables are null, so we will not make any recursive call. After adding the node 3 to the linked list, we do not make any recursive call to process the left and right child. Okay, so then we come back, and then we come back to frame 2, and there we check whether the right child is not empty. So in that case, the node 2 has the right child 4, so we make a recursive call to process this node. So at the end of this recursive call, the node 4 is added to the linked list. Since this do not have any children, we simply return back to frame 2, and since because the frame 2, in frame 2 we already processed the left and right child, so this in turn return back to frame 1. So so the left child is returning back to the root node. Okay, so in the root node in frame 1, we have right child is not yet processed, so we make a recursive call to process this right child, and which gets added to the linked list, and this node has a right child and do not have a left child, so we make a recursive call to process that right child, and that gets added to the linked list. So once that is done, the frame 3, from frame 3 we return back to frame 2, and in frame 2 we already processed the left and right child, so we eventually return back to frame 1. So when we come back to the frame 1, the root node is pointing to the node 1, and the last pointer is pointing to the node 6 in the linked list, which is the last node. So we can use the current root node as the head of the list, and to traverse the linked list by following the right child's pointer. Next, I'm going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. To create a linked list, we have to perform the pre-order traversal. So the pre-order traversal visit all the nodes in the tree. So in this case, we have 6 nodes. So the pre-order traversal makes 6 function calls to process each node. If there are n number of nodes, we have to traverse all the n nodes in order to build the linked list. So the time complexity of this algorithm is order of n. The space complexity analysis of this solution is order of n if we include the system's stack space usage in our complexity analysis. Otherwise it is order of 1. Okay. So when we do the pre-order traversal, we make a recursive call, and the number of frames in the call stack depends on the height of the tree. Okay, which in turn depend on the number of elements in the tree. So there are two cases. If the tree is complete binary tree, then the height of the tree is log n. If the tree is a skewed tree, then the height of the tree is n. If the input tree is a complete binary tree, then the space complexity is order of log n. If it is a skewed binary tree, the space complexity is order of n. So we take the worst case scenarios. So the space complexity is order of n. Thanks for watching this video. Have a great day.